Okay, because we're running out of time with the previous lecture, I went a bit fast here on this example. We'll revisit it now. Okay, so the first one anyway, this one, okay, we showed with the arrow diagram that it's not 1 to 1 because both 1 and minus 1 are sent to 1. So 1 is sent to 1 squared is 1, minus 1 is sent to minus 1 squared, and minus 1 by minus 1 is plus 1. So two things are sent to the same thing. It's not 1 to 1. It's not 1 to 1. And straight away then you can say it's not bijective. And then is it onto? No, because it doesn't hit any negative numbers. In particular, it doesn't hit minus 1. Later on in chapter 5, we're going to learn a bit more about coordinate graphs, and x squared looks like this. And so you can do horizontal line tests to tell whether or not it is 1 to 1 or onto. In particular, here we see if you go across at y equal to minus 1, you can see the graph doesn't hit it, so it's not onto, and you can see this one hits it twice. Say if this is y equal to 1, so you see 1 is sent to 1, and also minus 1 is sent to 1. Now if you want, so what I'm proposing here is that you fix the onto problem by just throwing out from the codomain all the negative numbers. So what this looks like is, in terms of this picture, you don't have to, this isn't in the codomain, so this just isn't in the picture, and you can see that every horizontal line hits the graph, so it does become onto, but this issue with it hitting it twice is still there, so it's not 1 to 1. Okay, and in terms of picture, here's your real numbers. Here is your positive real numbers. Real numbers, positive real numbers. There's no issue with minus 1 anymore because I'm just considering the positive ones, including 0. And my function as dash. But it's not 1 to 1. Because both 1 and minus 1 are sent to 1. Okay, so the other thing we can do is, okay, if we look at this graph, we can say, okay, what if, okay, we throw this bit out to fix onto. The issue is that it's hitting here again, so what about we throw that out, and our graph just looks like that. And that one, if you draw any horizontal line, it does cut it, and it cuts it only once, so it'll be 1 to 1 and onto. Now, how do we actually prove that? You can say, oh, I look at the picture, but can we do a bit better than that? So let's see how we do that. So here we're just going, this is called S double dashed, don't do derivatives or anything, it's just a notation. So is it onto? So what I do is I'll take a positive number, say y, and the question is it hit? And the answer is it will be hit by the square root of y. So if you square the square root of y, you get y. So y was, now this is algebra, which will be coming in the next chapter. So we're saying if you take any positive real number, any one at all, you can call it y, something will hit it, root y will hit it. So this shows that, this argument shows everything is hit. Which implies that S double dashed is onto. Okay, then the other thing we need is, or what we're interested in, is it 1 to 1? Now this is a bit harder, but basically what you do is you take two inputs, x1 and x2, and so here's two inputs, x1 and x2. Imagine them like this, x1 and x2. Is it possible that they both hit the same thing? So x1 is sent to x1 squared, and x2 is sent to x2 squared. Is it possible that they are actually the same thing? And to solve that, we're going to need algebra, and I think we're going to look at it later. And it's going to turn out that this function here is 1 to 1. If two positive numbers, remember these are positive numbers, have the same square, then the numbers actually have to be the same. So the picture doesn't look like this. It ends up x1 and x2 are the same, so it appears you have two different things, but it's actually only one. And we're going to learn in the next section, in the next lecture, that functions that are bijective can be inverted. And so when you talk about the square root function, it's not the language we're going to learn about is inverse. It's not the inverse of this one. It's not the inverse of this one. It's the inverse of this one. And so you get a slight difference between, so if I write down the equation x squared equal to 4, it really, there's two different possibilities, there's two things that's going on. Is x in the real numbers, in which case there's two solutions, or is x in the positive real numbers, in which case you only get 2. And the square root function is kind of this one, which is not the same as this, which we usually do. So the square root function isn't the same as the answer of this. So this is usually the meaning of this. So x is equal to plus or minus 2. Both of those numbers squared to give you 4, but the square root will only give you this one. So we'll talk about that a bit later. So what I'm going to do in this video after that is, so basically that's giving us the need for algebra down the tracks. We're going to give some hints and possible answers to some of these. Okay, because just so a bit of help. So this function here, this should be big F, by the way. How do you do this? Draw an arrow diagram. So this is the ordered pairs. So calculate. So f of 1, f of 0, f of 1, using this formula. Oh, I wonder, should this be minus 1? Yeah, I'd say this should be minus 1, minus 2, and this should be minus 1. I think it just copied and pasted around. F of 0, f of 1, f of minus 1. And then you should write as f equals to, say, 0 in, and then write out whatever the output was here. And do that for the others as well. Is it 1 to 1? Is it onto? Arrow diagram. Similar story here. Is this function vertical? This is actually in the wrong section. Next section. Okay. Is it a function, yes or no? Use the vertical line test. Is this a function, yes or no? Vertical line test. Is if it is a function, is it onto? Use the horizontal line test. Is it a function, yes or no? Use the vertical line test. If it is a function, is it 1 to 1? Use the horizontal line test. Show this function is not onto. But what you should do is so calculate the first few. So f of, say, so these are 1, 2, 3, 4, 5. Calculate f of 1, f of 2, etc. is every natural number hit. Like, do you hit 1, 2, 3, 4, 5? Is every natural number hit? You could do a little bit of arrow diagram work here as well, to a small degree, but the sets are infinite, so you can't list all of the elements. Now this is a harder question, so I'm going to leave this to people who want to push it a little bit. I would say maybe here what you do, so play around, but that wouldn't be a proof. Play around with, this is for both of them, small m and n, for example, like 2, 3, 4. See what happens. Remember, this means that A has m elements and B has n elements. So for example, look at some examples here. No, I won't do all the, better. So say A1, B1, A2, B2, A3, B3, A4, B4. So play around with, say, if this has 4, 1, 2, 3, 4, and this has 2, and play around with this has 2, and this has 4, this kind of thing. Just play around and maybe you'll be able to answer the questions then. Okay, next lecture.